Welcome to the Deep Dive. If you've ever used the internet to search for, well, anything, a cat video, directions across town, or even if you're training a huge AI model.
You've relied on the work of Jeffrey Dean.
That's right. Today we're diving into the career of, I think, maybe the most influential architect of modern computing that most people have never heard of. He's the chief scientist of Google DeepMind and Google Research.
And our sources trace this just incredible path. We're talking from 8-bit computers all the way to agentic AI.
So our mission with this deep dive is really to give you a shortcut to understanding the foundational substrate of the modern economy.
And here's the core idea we found. Dean's genius is what our sources call a systems-first approach to everything, even intelligence.
What did that mean exactly? A systems-first approach.
Well, you had all the theorists focusing on perfecting algorithms, but Dean saw something else. He realized the real roadblock to AGI wasn't just the math, it was physics.
Physics, you mean like latency, bandwidth?
Exactly. Latency, energy, and efficiency. His whole point was, if you can't build a system that can handle the computation at scale efficiently, the best algorithm in the world is useless. The intelligence just stalls.
So the problem wasn't what the computer was thinking, but how fast and cheap it could think it.
Precisely. And his entire career is just this relentless focus on optimizing every single part of the machine.
Okay, let's unpack this then. Because if he's famous for building the biggest systems on Earth, where did this obsession with, efficiency and engineering thrift even start?
It's a really unexpected origin. It started with public health, with epidemiology.
Right, he was born in '68, and his parents were in global health. One was an epidemiologist with the CDC, the other a medical anthropologist with the WHO.
And that is the key context. Epidemiology, tracking disease patterns, that really is the original big data problem.
You're not working with clean lab results.
Not at all. You're dealing with vast, messy, real-world data, and you're trying to find that one tiny signal in all the noise, like how a virus is spreading.
And he was building software for this stuff in high school.
Yeah. He worked on a statistical package called epidemiology. It was for the WHO's global program on AIDS. Now, think about the constraints here.
This isn't running on a supercomputer in a lab.
No, this is running on very modest hardware in field clinics. In Africa, in Asia, it had to be absolutely rock solid, and it had to handle all sorts of messy data schemas.
Building reliable software for the WHO on an 8-bit machine. That sounds like engineering under extreme pressure.
It instilled two things in him. First, what you could call the discipline of scarcity. Every single byte, every clock cycle mattered.
And the second?
Population-level thinking.
Yeah.
He wasn't just solving for one computer. He was designing a system that had to work across a whole population of unreliable machines. And that thinking, whether it's a population of humans or a population of 10,000 servers, it's the same mindset.
And that adaptability must have been reinforced by his education. The sources say he went to 11 different schools.
Right. It's like a compiler having to adapt to new hardware all the time.
Let's not forget the hardware itself, the crucible of his youth. We're talking about machines like the TRS-80.
The Epson QX10 running CP/M. These are 8-bit machines. You had to manage memory by hand.
A bad program didn't just slow down, it crashed the whole thing.
Exactly. That hands-on intimacy with the bare metal, it just hardwired him to optimize everything. It never left him. That famous list he made.
Latency numbers every programmer should know.
Yes, where he breaks down the actual physical time cost of a memory lookup versus a disk seek, that is a direct line back to him counting clock cycles on his first computer.
So that deep physical understanding of how much things cost in time and energy, that sets the stage for his PhD work at the University of Washington. He moves on to compilers.
Which seems like a huge leap, but there's a fascinating link. He was tackling the big problem of the 90s. Object-oriented programming. It was powerful, but it was notoriously slow.
Because of something called dynamic dispatch?
Right. The compiler couldn't predict which bit of code would run next, so it couldn't optimize well.
So he looked at this software problem with a systems brain.
He did. His thesis led to the Vortex compiler. And his big idea was whole program optimization. Instead of looking at code file by file and making conservative guesses,
He looked at the entire program at once.
as one giant graph of dependencies. And by seeing the whole map, he could find these incredibly aggressive optimizations like selective specialization that made OOP actually fast.
Okay, this is where it gets really interesting. He learns to see code as a massive, interconnected graph. So how does he take that idea and apply it to the biggest graph of all, the entire World Wide Web?
That takes us to Google from 1999 to about 2012. He and his collaborator, Sanjay Gamawat, they arrive, and Google is facing a physical crisis. It's growing too fast.
And the old model of buying these giant, expensive mainframe computers wasn't going to work.
It was dead, so they pioneered the commodity cluster. Thousands and thousands of cheap, off-the-shelf PCs.
That were designed to fail.
That was the radical shift. Move reliability from the hardware, which you know is going to crash.
Up into the software?
Exactly. The software had to just expect constant failure and be able to recover instantly. This thinking gave us the 3 pillars of the modern cloud.
Pillar 1, MapReduce in 2004.
MapReduce basically made large-scale parallel computing accessible. It boiled these massive jobs down to just 2 simple steps, map and reduce.
But the runtime system did all the heavy lifting, the load balancing, and crucially,
the fault tolerance. If a machine died mid-task, the system just shrugged and reassigned its work to another machine. It democratized scale.
Then came BigTable in 2006, the NoSQL revolution.
Don't think of it as a rigid database. Think of it more like a giant, globally distributed spreadsheet that could adapt to anything.
Sparse, multidimensional.
The key was flexibility, no rigid schema. That's what allowed products like Search and Maps and Gmail to evolve so quickly.
And that leads to the really big one, Spanner, in 2012. This was designed to do something that theory, the CAP theorem, basically said was impossible.
It was. They wanted to provide external consistency, true linearizability. It means every user on Earth sees every transaction in the exact same order, no matter which data center they hit.
And their solution for this, TrueTime, it sounds like science fiction.
It kind of is. They didn't solve a software theory problem with more software. They solved it with hardware.
They put GPS receivers and atomic clocks in every single data center.
Right. So normal computer clocks drift. But with TrueTime, they could know with absolute certainty the tiny window of that drift, the uncertainty interval.
So they know exactly how uncertain they are.
Precisely. And when Spanner commits a transaction, it just waits. It's called the commit wait. It waits for that tiny interval, maybe 7 milliseconds, to pass. And once it has, the laws of physics guarantee no other machine on the planet could have seen that transaction happen earlier.
They beat a theoretical limit with physics.
They did. These systems, MapReduce, BigTable, Spanner, they are the invisible ground we all walk on every day.
So by 2011, Dean has basically mastered organizing explicit data, text, maps, numbers. But the web is becoming visual. It's becoming auditory. And this leads to that famous meeting in a micro kitchen.
The perfect collision. He runs into Andrew Ng from Stanford, who's a pioneer in neural networks. Ng has the algorithms, but he needs massive, massive compute.
And Dean has the systems.
And Dean instantly gets it. He sees that computational scale is the missing ingredient, and that insight becomes Google Brain.
Which leads to the iconic 2012 cat neuron paper.
A landmark, absolutely. They took 16,000 CPU cores and just unleashed them on 10 million unlabeled images from YouTube. The scale was it was unheard of.
And the result was that a single neuron in this massive network taught itself to recognize cats.
Without any human labels, it just saw enough of them and figured it out. It proved that unsupervised learning could extract these high-level concepts if and only if you had enough scale.
And to manage that scale, they built their first distributed training system, Disbelief. But that success immediately created the next problem, didn't it? The next bottleneck.
It did. Dean did one of his famous back-of-the-envelope calculations around 2013, and the number was shocking.
What was it?
He figured if every Android user used voice search for just 3 minutes a day, Google would have to literally double its number of data centers every single year.
Just to keep up.
Just to keep up. Standard CPUs were just too slow and too power-hungry for deep learning.
So he goes from optimizing software to actually designing the silicon. He becomes the champion for the tensor processing unit, the TPU.
The TPU is the ultimate example of hardware-software co-design. They built the chip to do one thing perfectly: the math of neural networks. It uses a design called a systolic array.
Instead of constantly fetching data from memory, which is slow and uses energy,
the data just flows through this huge grid of multipliers like a pulse. It drastically cuts down on data movement, which is where most of the energy is wasted.
and the performance gains were just absurd.
Oh, they were staggering. The first TPU was 15 to 30 times faster for inference and up to 80 times more power efficient.
Which then allows them to open source TensorFlow in 2015. And it represents computation as a
data flow graph, exactly like his PhD work on compilers 20 years earlier. It was the perfect way to map these huge computations onto all this different hardware CPUs, GPUs, and now these new TPUs, the the circle was closing.
So as we get into the 2020s, the training problem is more or less solved, but Dean spots the next big inefficiency: dense models. It's wasteful to use a whole trillion parameter model for every single query.
Right. And this leads to his philosophy of pathways starting around 2021. The goal was a system that was sparse and multimodal from the ground up.
And the architecture for that is called Mixture of Experts, MOE.
Right. So instead of lighting up all 1 trillion parameters, a little gating network at the front looks at the query.
And sends it to only the relevant experts.
Only the 1 to 5% of the model that actually knows about that topic. It makes these giant models computationally feasible and way more efficient.
And that pathways idea is what's driving the Gemini project today,
Right.
where he's now chief scientist of the combined Google DeepMind.
And you can see the shift in the latest versions. They're moving from just a chatbot to what you might call an agent.
It's not just about the answer anymore, it's about the reasoning.
Exactly. The agentic part is key. The model can now write and execute its own code to check its work. It closes the loop between thinking and doing.
Which brings us to what might be his most forward-looking and maybe most radical idea: AI for systems. This one I find just mind-bending.
It's probably the most subversive idea in computer systems in decades. I mean, for 50 years, the guts of our computers' operating systems, compilers, databases, they've all been built on human-written rules, heuristics.
Hard-coded in C++ or Java.
And Dean's argument is that those human rules are just crude, suboptimal models of the world.
He has this great example with database indexes. We use something called a B tree.
Right. A B tree is just a set of rules for finding where data is stored. But in a 2017 paper, he showed that a simple neural network could just learn the pattern of the data. It could learn the index.
And the results?
They were stunning. 70% faster lookups, and it used an order of magnitude less memory than the traditional B tree.
So what does that mean going forward? What's the future he's pointing to?
It's a future where the core components of computing aren't static code anymore. Your operating system, your compiler, your network protocols, they become fluid, self-optimizing machine learning models.
So the AI is building and running the system that enables the AI.
It's the ultimate recursive optimization.
That level of engineering is so respected, it famously spawned the Jeff Dean facts meme inside Google.
Compilers don't warn Jeff Dean. Jeff Dean warns compilers. I mean, they're funny, but they point to a real culture he created.
The culture of the back-of-the-envelope calculation.
Yes, forcing engineers to actually estimate the cost and scale of something before they start writing code. That's his real cultural legacy.
Our sources also point out that later in his career, he's become more public about societal issues. There was a notable clash in 2025 with Elon Musk on X regarding U.S. immigration policy.
That was significant. You saw this famously quiet systems architect using his reputation for data-driven precision to weigh in on major policy debates. It was a real shift.
So when you trace it all, from beginning to end, his whole career is just one principle applied over and over.
Optimization at scale. He optimized compilation, he optimized web search, he optimized neural network training, and now he's trying to optimize reasoning itself.
And what he really proved is that systems and AI aren't different fields.
They're the same discipline. The intelligence of your model is ultimately a function of the quality of the system that builds it.
And that leaves us with our final provocative thought for you. If our future operating systems and compilers are no longer static code, but are fluid, self-optimizing ML models, what happens to the job of human engineering when the system starts to design itself? Where does that leave us?
And we highly recommend you look up True Time. It is just a brilliant example of how a team defeated a theoretical limit like the CAP theorem, not with better algorithms, but with better physics, with atomic clocks.
An incredible deep dive. We hope this gave you a shortcut to understanding the architect of our planetary scale world.
Thanks for tuning in.
We'll see you next time.